Hi everyone, welcome back. So in this video, we're going to be talking about bifurcations again. So remember that in chapter 2, we also discussed bifurcations which are changes to the stability of a dynamical system when some parameter changes. In chapter 2, we were talking about difference equations. Here in section 5.8, we are, of course, going to be talking about bifurcations in differential equations. So let's go ahead and get started by just looking at first order equations. So not systems of equations, just single first order equations. Bifurcations in first order equations. And it turns out that this is going to look very, very similar to the bifurcations in first order difference equations. Let me make that clear. Differential equations. Okay, so we're going to start with the usual setup. Let's let dx dt be equal to some function f of x r. So this is going to be an autonomous system where r is the bifurcation parameter. And x bar of r is the set of equilibria given some value of r. Okay, so we're going to first start by reminding you of three types of bifurcations. So you can compare this against section 2.7, where we did the same thing basically, with one very, very important difference for difference equations. First, well, let's start with our saddle nodes. Our saddle node bifurcations. I prefer to call these blue sky bifurcations since they appear out of nowhere and appear and disappear out of nowhere. So if we start with that, we have the r-axis and the x-axis where we're going to be graphing out x bar of r. And these are things where you start out where you have let's use the dotted line to refer to unstable equilibria and the solid line to refer to stable equilibria. And this is when you have two equilibria that come together and disappear. And note that one of the equilibria you're starting with is unstable, the other one is stable. They come together, and at some point, they disappear and go poof. Alternately, if you look at it from the other direction, if you're starting from, you have nothing, and then all of a sudden, poof, you appear a pair of equilibria that separate from out of nowhere. And let's give an example of this. So this is the canonical example. dx dt is equal to r plus x squared at r is equal to 0. So first, what does it mean for there to be an equilibria? So in order to solve the equilibria, we set dx dt equal to 0, right? So 0 is equal to r plus x bar squared, which implies that x bar is equal to plus or minus the square root of minus r. Which is real when r is less than or equal to 0, and x bar is equal to the empty set when r is greater than 0. Oh, sorry, you can't read that. When r is greater than 0. Let me rewrite this just to make it a little bit more clear. When r is greater than 0. Okay. And therefore, we also know that if f of x is equal to r, let's call this f of x. I guess this is f of x r. So if we holding r constant, so holding r constant, let f of x be equal to r plus x squared, and so then f prime of x is equal to 2x, which implies that f prime of square root of minus r is equal to 2 times the square root of minus r. And so this is going to be the case when r is less than or equal to 0, because otherwise, well, then the equilibria doesn't exist, so we don't care about it. So this is greater than 0, so unstable. Alternately, f prime of minus the square root of minus r is equal to minus 2 times the square root of minus r, which is less than 0. So this is stable. And so these correspond precisely to the two different, These correspond precisely to the two different equilibria that we see over in our graph there. So they start out, the top one is unstable, the bottom one is stable, they come together, they go poof, and then all of a sudden, no more equilibria. Okay, so that was one of the equilibria that we saw with the difference equations. Let's do the second one. So we also had pitchfork bifurcations. So we had two different types of these. One of them are the supercritical ones, and the other ones are the subcritical ones. Just a moment, let me draw a straight line. Okay, so with one of them, we start out with a stable equilibrium, and then it turns unstable while branching off into two different stable chunks. And so this is why it's called a pitchfork, because it looks sort of like a sideways pitchfork. Ultimately, you can also start out with an unstable equilibrium. It branches off into two unstable wedges, while the equilibrium at that location turns stable. So let me actually write, so stable, 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 unstable, 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 and stable. Okay, so and this one here is supercritical, and this one here is subcritical. So the subcritical one, you start out with an unstable equilibrium, and it turns into three equilibria. The middle one is stable, the other two are unstable, and vice versa for supercritical equilibria, supercritical pitchfork bifurcations. So let's give an example of this, and this will be this example, as we'll come to see. So we start out with dx dt is equal to rx minus x cubed, which is f of xr. Okay, so then we have 0 is equal to rx bar minus x bar cubed. And so 0 is equal to x bar times r minus x bar squared, which implies that x bar is equal to 0 or plus or minus the square root of r. So then letting letting f of x be equal to rx minus x cubed for r constant, we get f prime of x is equal to r minus 3x squared, and therefore f prime of 0 is equal to r. F prime of square root of r is equal to r minus 3r, which is equal to minus 2r. And the same for f prime of minus the square root of r, because you're taking a square, and so the minus sign doesn't matter. And note that these are only things we care about for r greater than or equal to 0. And so what you see here is that the zero equilibrium... Oh, I keep on hiding the text today. Sorry about that. So what you see now is the zero equilibrium. The sign of the first derivative of the zero equilibrium is the same as the sign of r. So it starts out here where it's stable because r is less than 0, and then it becomes unstable. On the other hand, for f prime of the plus or minus square root of r branches, well, those both have first derivative that's minus 2r, so the stability is So it's stable when R is positive and unstable when R is, well, it doesn't exist when R is negative. And so you get these two. Oh, sorry. You get these two branches. Okay, and we have, you should be expecting the next one now. So the next equilibrium is going to be the let me move that down a little bit more. I think I was using blue for that. Yes, I was using blue. So the next equilibrium here is going to be the transcritical equilibrium. Transcritical bifurcation. And here, as before in section 2.7, what you do is you start out with a pair of equilibria, one of them stable, one of them unstable, one of them unstable, one of them stable, and then the stable equilibrium, they cross, and at the crossing point, the formerly unstable equilibrium becomes stable, and the formerly stable equilibrium, they switch stability. So here we have unstable, stable, and then unstable, and stable. And let's also give an example of this one. So let me write it over here. So we have let's say dx dt is equal to r x plus x squared. And so let's let f of, I'll do that in a moment. So then 0 is equal to rx bar plus x bar squared. 0 is equal to x bar times r plus x bar. So x bar is equal to 0 and minus r. And we're going to let f of x be equal to rx plus x squared for our constant. And that implies that f prime of 0 is equal to r, and f prime of minus r happens to be equal to, let me actually write out the first derivative. So f prime of x is equal to r plus 2x. And so that makes it really easy. So f prime of 0 is just equal to r, and f prime of minus r is equal to minus r. And so again, for the 0 equilibrium, when r is negative, it's going to be stable, and when r is positive, it's going to be unstable, and vice versa for the minus r equilibrium, which is the example graph we showed over on the left. Okay, so now let's go ahead and move on to systems of ODEs and the Hopf bifurcation. So at this point, you should be wondering, if you've been paying attention, what happened to the fourth equilibrium type that we had with difference equations. So when we were talking about difference equations, we had these three equilibria: the saddle node, the pitchfork, and the transcritical bifurcation. But we also had a fourth. So what happened there, and why didn't we give a fourth bifurcation type for above for the first order ODE? Well, there's a really good reason for that. So what was that fourth bifurcation? So that was the period doubling bifurcation. Bifurcation for difference equations. So now that this is for difference equations, and what did that look like? So that looked something like this, where you start out with a, let's say, you have an equilibrium, which starts out, let's say, stable at one point, and then becomes unstable. And then what happens is it branches off and turns into a 2-cycle. Or if you start out with a 2-cycle, it branches off and turns into a 4-cycle. But first order ODEs can't be periodic. So this is inapplicable. Right? Because you can't have a period doubling bifurcation if you're not allowed to be periodic. And so in order to get the appropriate generalization of the period doubling bifurcation, or the appropriate analog of the period doubling bifurcation for differential equations, we have to turn over and move on to systems of ODEs, since they're higher order, and you can actually have periodic solutions for systems of ODEs, though you can't for a single first order ODE. And to that end, let's go ahead. This is a little bit more complicated, but let's define the Hopf bifurcation. So I'm going to define a little bit hand-wavy here, but a Hopf bifurcation is a critical point where stability changes, so standard thing, where stability changes, and a periodic solution appears. Or disappears, depending on which way you're going. But so this is going to be a Hopf bifurcation. And let's start out by trying to understand this with a really simple basically linear example. And this is going to be example 5.19 in the textbook. And then we're going to generalize it because this is a little bit more complicated to understand. So let's start with this linear system where dx dt is equal to rx minus y, and dy dt is equal to x plus ry. And so we can also rewrite this as x dot of t is equal to r minus 1, 1 r x of t, where x of t is equal to, well, x of t and y of t, little x of t and little y of t. And since this system is linear, it's pretty easy to find the Jacobian matrix, right? So the Jacobian matrix is actually just going to, at any point, is going to be just this matrix here. And so therefore, the Jacobian matrix at 0, 0 is going to be equal to r minus 1, 1 r. And if you compute the eigenvalues of this, this is going to have eigenvalues of r plus or minus I. Okay? And so now let's consider different cases. So we can, now we have this, we know what the eigenvalues are, and it turns out that, let's list the cases. So if r is less than 0, then 0, 0 is a stable spiral. And we also have if r is greater than 0, then 0, 0 is an unstable spiral. And lastly, if r is equal to 0, well, this is a linear system, so we can go ahead and use the linear system classification. Then 0, 0 is a neutral center. And it turns out that in this case, we have infinitely many neutrally stable closed orbits, right? Because in this case, we around equilibrium. Basically, all the circles going around the origin count here. Okay, so let me draw that out. So here we have our let me draw that a little bit better. So here we have a stable spiral, so everything goes in. Here we have an unstable spiral, so everything goes out. And here we have a neutral center, so things go in circles around it. Let's see, actually, let me do all of this in a different color, just so that, since I'll be using colors very deliberately in a little bit. So we have our neutral spiral, we have our stable center, so and we have our unstable spiral. And so this is one of the things that can happen. So this implies that. So you'll notice that at r equal to 0, well, periodic solutions appear. They disappear immediately, which is a little bit weird, since but they do appear, and so this is a Hopf bifurcation. I'm actually going to call this a degenerate Hopf bifurcation because the periodic solutions disappear immediately. At r equal to 0. And so this isn't the only behavior that can happen. Let's go ahead and classify the behavior of Hopf bifurcations. Classification of Hopf bifurcations. And one of the things we'll see is that in this particular case, our bifurcation happened, and so a stable spiral turned into an unstable spiral, but at the moment of the bifurcation, you suddenly had an infinite number of neutrally stable orbits. Now, well, in the general case, what will happen is you won't, at one single moment of one single value of r, have an infinite number of different periodic solutions. Instead, what will happen is well, we'll see. It'll be a little bit easier to draw out. So let me do that in a moment. So for this, there are several different cases. So the first case, let's call it the degenerate case, which is the one above. And let me just write this down again. So at bifurcation value, infinitely many neutrally stable. So by that I mean solutions don't get closer to it and don't get farther away. Closed orbits around equilibrium. And so now, if you look up here, these are in the xy plane, right? So this is the phase portrait. So that's a 2D plane. Now, if I want to draw out, whereas up here I had the, well, this is the x plane, this is the r plane, and this was the x and the r, x and r, x and r. So this was a bifurcation plot where you're plotting out your variable x against your bifurcation parameter r. But now we have two variables. So unfortunately, this means that we need to draw a plot in 3D if we want to draw out the bifurcation diagram. So what does that look like? And it's going to be a little bit more complicated, so hopefully my art skills are up to snuff. And they really aren't, but hopefully this will not be too confusing. So instead of being in 2D, we're going to be in 3D. So this is going to be our r-axis, this is going to be x-axis, and this is going to be our y-axis. And we're going to plot the bifurcation diagram. And so what happens? So up here, if r is less than 0, then it's a stable spiral. So this is a stable spiral. It's a stable equilibrium. And if r is greater than 0, this is going to be an unstable spiral. Okay, so stable spiral at 0, and unstable spiral at 0. And now the key here is that at the point xy equal to 0 and r is equal to 0, you have a center. So this is a neutrally stable center, and so at that point you have a bunch of orbits, infinitely many orbits that appear at neutrally stable orbits at r is equal to 0. And this is because what we're basically doing is we're taking these circles up here and we're putting them sideways in this xy plane, and at r is equal to 0, you have these neutrally stable circles. So, yeah. So now what we're going to do instead is, instead of having these neutrally stable, so this is not the typical case. This only happens if you balance your parameters really precisely, or if you're in the linear case as we were for the example. Usually what will happen is these concentric circle disks will actually be smeared out across. So let me draw that out to make that a little bit more obvious. So the second case, this is the supercritical case. So in the supercritical case, what happens is, let's see, we have our x, y. So this is x, this is y, this is r. And you start out with, let's say, a stable spiral. And then you turn it into an unstable spiral. But what happens instead is, let's use the color green. So let me draw this out a little bit further. So what this is I've taken each of these concentric circles and I've smeared them out across the positive positive part of for positive r. And so you have a cone of stable limit cycles. You have a cone of stable limit cycles instead, and of course you still have your stable spiral and your unstable spiral. So what do those look like? So for r is less than 0, so for r less than 0, let's say at a point right here, what we have is just the usual case. So trajectories go inward. Let's draw a couple more of them. And for r is equal to 0, and I'm not going to draw r equal to 0 since at r equal to 0 sometimes weird stuff happens. But let's draw, let's see, r less than 0, and let's draw another point, let's say here. So for r greater than 0, what it looks like instead is you have your equilibrium still, and it's an unstable spiral, but you have a circle around it, which is a stable limit cycle. So what does that mean? This means that trajectories that appear here will go outward and approach this limit cycle. So you get closer and closer to this. Oh, sorry, let me scroll this up so you can see. So you have your equilibrium in the middle there at the 0 point, and you have a limit cycle which surrounds it. And as you get further and further, as you go away from your equilibrium, because it's an unstable spiral, you approach your limit cycle, but you don't ever cross it. And on the other side of the limit cycle, you might have a point that starts here and then gets closer and closer to the closer and closer to the limit cycle from the outside. So it's a stable limit cycle, and you have trajectories approaching it from both the inside and the outside. Okay, and sort of what we've done here is we've taken each of our these concentric circles up here and we've spread them out. So instead of them all appearing infinitely many at the at the bifurcation point, instead they're spread out across multiple values of r. And of course we also have the subcritical one, which is just going to be the opposite. So subcritical, where you just flip the stability of everything. But let me draw it out just so that we're all on the same page here. So here's our r-axis, our x-axis, our y-axis, and let's start out with a unstable spiral and then a stable spiral instead. So we start out with an unstable spiral, and we end with a stable spiral. And what happens along here? Well, you have the same cone of limit cycles, but this cone is now a cone of unstable limit cycles. Okay, so cone of unstable limit cycles, which means that you're not actually going to approach it if you start from anywhere else. You're only going to approach it if you actually start on the limit cycle, because otherwise you get exponentially far away since it is unstable. But what does this look like? So if we have these 2 points here, those ones are less than 0, the other ones are greater than 0. So for r less than 0, we have an unstable spiral. So that's just standard. And for r greater than 0, what do we have? Well, let me scroll this up. So we have our we have an equilibrium, and then we have a circle around it. So this is the unstable limit cycle. Actually, I guess I should draw this in dotted lines. So this is our unstable limit cycle. And if you start near the unstable limit cycle on one end, you come in to the 0 point. And if you start on the, so things get closer to, and this is a stable spiral, and if you start near the unstable limit cycle, you're going to go away from it. And if you start near the unstable limit cycle on the other end, you're going to get further and further away. Okay? So this is basically smearing it the other direction, where you're smearing it to the left instead of smearing it to the right. Okay, and so this is the sort of higher dimensional, the two-dimensional analog, and this appears in higher dimensions as well, to the period doubling bifurcation, which we saw in the difference equations. But of course, we can't deal with, we don't have any sort of periodic behavior in a single first-order ODE. So instead, we have to look at these period-generating bifurcations, these Hopf bifurcations in at least R2. And so we're drawing the pictures in R2, but of course this also applies for higher dimensions where you have like n different differential equations. And the key point here is that near the bifurcation point, you end up with some periodic solutions. Sometimes those periodic solutions are all at the exactly r equals 0, so this is a degenerate case. But usually, what will happen is there'll be you'll end up turning a stable spiral into an unstable spiral and a cone of stable limit cycles, or an unstable spiral into a stable spiral and a cone of unstable limit cycles. Okay, so that was all pretty generic. Let's talk about this a little bit more rigorously. So I'm going to give you a super rigorous theorem statement, and note that it's a little bit hard to apply with all the conditions I'm going to put on this, but I'm going to give it to you in generality, and then I'm going to give you a simpler version of it that's a little bit easier to manage. So let's start in full generality. So let's consider the system dx dt is equal to some function f of x, y, and r. And we have dy dt, which is also some function g of x, y, and r. Or equivalently, we can also write that as x dot of t is equal to x dot of t, y dot of t is equal to f of x, y, and r, and g of x, y, and r. Okay, so having said that, without loss of generality, assume the origin is an equilibrium. The origin 0, 0 is an equilibrium. And if not, otherwise, just translate the coordinates. Translate coordinates. So change the variables, make the 0 point the equilibrium, because otherwise it gets even more complicated to talk about. So we can then rewrite the system, separating out the linear terms. So we have dx dy is equal to a11 of r. So this is some term that's linear in x or y, but may not be in r, since r is some parameter. A11 of r times x plus a12 of r times y. And plus, well, you have something left over, right? So let's call this function f1 of x, y, and r. And dy, that was dx dt. And we have some other function dy dt, which is going to be a21 of r times x plus a22 of r times y plus some function g1 of x, y, and r. So this is equivalent to rewriting as x dot of t is equal to some matrix a11 of r, a12 of r, a21 of r, a22 of r times x of t plus another vector, which is these higher order remainder terms, f1 of x, y, and r, and g1 of x, y, and r. And so because we've separated out the linear terms, we can assume that the Jacobian, j of r, is equal to these terms, a11 of r, a12 of r, a21 of r, and a22 of r, is the Jacobian at the origin. At 0, 0. And this expression is basically valid for any small r. Small. And you can double check that this makes sense based on the actual definition of a Jacobian and plugging in 0, 0. What you'll find is that the higher order terms, well, they won't, the x and y's won't disappear from them for when you take the partial derivatives, and therefore they'll be canceled out when you evaluate at the origin, which is why we chose 0 to be the origin, to be the equilibrium point, which makes this decomposition work out nicely. Now, in order to actually prove this theorem, which we are not going to do, you're going to have to assume that f1 and g1, so these remainder terms, have continuous third order derivatives. Continuous third derivatives in x and y. So continuous partial third derivatives in x and y. This is just a technical constraint, which we're not going to worry about too much. And in addition, assume that once we have this matrix, that alpha of r plus or minus I beta of r are the eigenvalues of j of r for small r. For r with small absolute value. And yeah. And we're going to assume that alpha of 0 is equal to 0, and beta of 0 is not equal to 0, such that the eigenvalues cross the imaginary axis with non-zero speed. What do we mean by that? Or more precisely, what we mean is d alpha dr. Alpha is a function of r, so we take the derivative of that with respect to r, evaluate at 0, that's not equal to 0. So the alpha is actually crossing the imaginary axis. Len, so if you start with all these assumptions, len in any open set U in the plane, such that includes the origin, and for any r not greater than 0, there exists some r bar such that r bar is less than x naught, such that there exists a periodic solution. A periodic solution for r equal to r bar in U. And it turns out this periodic solution has an approximate period of t equal to 2 pi over beta of 0. Okay, so now that is a super technical theorem, which we are not going to prove, but let's try to explain a little bit more intuitively and give you something that's a little bit more workable. So intuitively, what we mean to say is that if we consider the Jacobian matrix, so just the regular Jacobian, not defined in that weird way, Jacobian at the equilibrium, at the origin of the at the origin where the origin is an equilibrium. And let's actually call this J of R, because it is going to be still, no matter what, it's going to be dependent on your parameter R. So if at R equal to 0, eigenvalues are purely imaginary, but the eigenvalues have differently signed non-zero real parts for R less than 0 and R greater than 0, then there is a Hopf bifurcation. So what are we talking about here? So this is a little bit confusing, but basically if you plot out the real imaginary axes, so this is the real axis and this is the imaginary axis in the complex plane, well, you know that your eigenvalues come in conjugate pairs, right? So you might have an eigenvalue alpha plus beta I and alpha minus beta I. And what we're saying is that as your parameter R changes, so those eigenvalues might move. So if they move across the plane, if they move across the imaginary axis, then what we're left with here is a new alpha plus beta I and new alpha minus beta I, where your alphas are negative. And if this happens, then you have a Hopf bifurcation, because at 0 you need just purely imaginary. And then as you go across, you go into the negatives. So what we're saying is that as the parameter R changes, the eigenvalues change. And at the parameter R equal to 0, we need the eigenvalues to have a 0 real part and have a positive or negative real parts on either side of the bifurcation. And so if this is the case, then you have a Hopf bifurcation. Okay, and let's give an example, because without examples, this is a little bit complicated. So let's give an example of the Hopf bifurcation. And we're going to give the example of dx. We saw one for the linear case, but that was a degenerate one. So let's see a non-degenerate one. Rx plus y and dy dt is equal to minus x plus ry minus y cubed. Okay? And so this has a Jacobian matrix, J of x, y, r, which is equal to r1 minus 1 and r minus 3y squared. And so at the origin, J of 0, 0, oh sorry, why did I put z there? That should be an r. 0, 0, r is going to be equal to r1 minus 1 and r. So lambda 1 and 2 are equal to r plus or minus I. So by the Hopf bifurcation theorem, note that when r is equal to 0, obviously your eigenvalues have, well, 0 real part. When your eigenvalues are positive, they have positive real part. When your when r is positive, you have eigenvalues with positive real part, and when when r is negative, you have eigenvalues with negative real part. there is a Hopf bifurcation at r is equal to 0. And let me go ahead and plot these out. I'm going to use Wolfram alpha to plot these out, and let me show you what those look like. So to visualize this, let's go over to Wolfram alpha and do a couple of stream plots just to see what these trajectories look like. So let's go over to Wolfram alpha, and I am going to do a stream plot of this function. So this function is rx plus y minus x plus ry minus y cubed. And let's look at it over the interval from x is equal to minus 2 to 2 or 2 to 2 for r is equal to 0.5. And when we do this, what you'll notice is that you end up with this stable limits, the stable limit cycle. So as you're going down on both sides, you go close to this cycle here. And if you're on the inside, it's an unstable spiral, and you're going out towards this limit cycle here. And note that this limit cycle isn't a circle. It has some weird nonlinear shape. On the other hand, if you look at r is equal to minus 0.5, instead, you don't have the limit cycle anymore. Instead, everything just goes in towards your stable spiral at the center. And if you want to look at what the behavior at 0, so note that this is the behavior at 0 isn't as generalizable. We can still take a quick look at it. What you'll see is that at 0, you start seeing this limit cycle appear. So what happens is your unstable spiral sort of, if you think about it infinitesimally as a point, it sort of expands out into a stable limit cycle with an unstable spiral at the center pushing out. And so that's sort of what happens with these kinds of Hopf bifurcations. And let's go ahead and copy and paste some of these things back over into our notes, just so that you have that accessible. But this is something that you should be clear about doing. So you can use this text here, and you can see these sorts of stream plots in Wolfram alpha, which makes it a lot easier to visualize some of these bifurcations. Let's go back over to the iPad, and so let's come on. So we have r is equal to minus 0.5. We have r is equal to 0, and we have r is equal to 0.5. Where you can sort of see this behavior as you go through your bifurcation point, and your stable spiral expands out into a stable limit cycle with an unstable spiral at the center. And yeah, so hopefully that was, actually let me go ahead and type in the command into my notes here as well, so you have that. Okay, I just copied in the Wolfram alpha command that you would need to copy and paste in to get these kinds of plots, and hopefully you can adapt that for other purposes, like on other examples of Hopf bifurcations, to visualize it and get a sense of what's actually going on from an intuitive and visceral perspective, as opposed to just looking at the super complicated theorems that we sometimes provide. So having said that, that ends this video, and I will see you next time.